Hi students, my name is Nathan Quinlan. I'm a lecturer in mechanical engineering. My email address and my Twitter handle are there if you want to contact me about anything. Welcome to NUI Galway, welcome to engineering, and well done on choosing it. It's been a rough old year. However you've come here, whether you finished school this year or you're coming in by a different route, you've dealt with quite a lot this year and you've done well to make it this far. So it's going to be a strange year. We are doing our very best to make it a good year and a good start to your engineering career. So what is a Geec? The Geec is the Galway energy efficient car. It started in the summer of 2013. A few of us heard about a competition called Shell Eco Marathon, which is a competition for engineering students to build cars and compete to find the most energy efficient cars. And they are not just the most energy efficient cars built by students, they are the most energy efficient cars in the world. And it is a global competition. There is a round in the Americas and a round in Asia and a round in Europe. So it took a while to get this off the ground. We found some students who were interested in having a go, who thought like us, what's the worst that could happen? What could possibly go wrong? We got them together, and the following year, in the autumn of 2014, they produced a car, which we were, very proud of. Very exciting moment to roll out this car. By the end of that academic year, so really 2 years into the project, they were ready to compete, and they went to Shell Eco Marathon Europe in Rotterdam. Now, we were not prepared for this event. It felt like arriving at a Formula One race or at the Olympics, except everybody is an engineer. Everybody is a geek with a K. Everybody is totally into what they're doing. There is an enormous hall where every team has their cubicle, their little garage. You can see the Geek's garage down there at the bottom left. There is racing all day. There is work going on in the garages literally all day from 7 a.m. Until midnight, until the teams were kicked out of the paddocks. The way the race works is that you go out on track in your slot. You are out there with all the other cars competing in your class. You have to find your own space on the track. You race 15 kilometers, which is 8 or 10 laps, depending on the course. You have to complete it at an average speed of at least 25 kilometers an hour. As long as you're above that average, it doesn't matter how fast you go. And the winner is the car that uses the least amount of energy, quite simply. So there are different classes of cars, different classes in the competition. There's petrol class, there's a diesel class, there's a hydrogen class, and there's battery electric, which we are in. And there's also prototype and urban concept. So urban concept are more realistic cars, more roadworthy cars, four-wheeled cars. Prototype are the silly cars where there are really almost no limits on the design. You design all out for ultimate energy efficiency. So the best way to show you what this is like is to show you a video.
Feels like the Olympics here, like we're over in the campsite and you can see all the other countries have got their flags up. Everyone's really excited to be here. This has all been building for about 2 years. We were approached, would we like to become the first Irish team to participate in the Eco Marathon? And once we talked it over with a few colleagues in the university, it was a resounding yes, and then we presented it to the students and we got a huge response from the students, so they've really driven this on. The students, I think, are really learning how to apply engineering and really make a project work and take it all the way to execution.
I'm only in first year, so it's kind of, a lot of it would be more technical than I would have done before, but it's really, really interesting.
We've got 17 undergraduate students on the team. we've got 2 postgraduate advisors, and we've got 3 academic mentors. And we're broken down into teams who deal with the aerodynamic aspects of the car, the mechanical aspects, the electrical aspects, and the electronic and sensor aspects. We had a day of testing where we really, for the first time, drove on conditions that we would be encountering during a competitive race, and that was a really eye-opening experience for us, and the car performed extremely well.
It's actually really nice to drive. It's easy to drive, it's easy to steer, it's not hard to control, so no, it's easy enough.
We've talked to loads of other teams. They're all really nice and they're really helpful. They also are really open about, different ideas and concepts that they have with their cars and sharing them with us and how to improve it and that.
It's been far more than any of us could have expected, and to actually be here and feel the energy of the other teams around us, it's just been incredible.
The NUI Geec team will be there in London next year.
We feel it'll give us a slight advantage over some of the continental teams, that it'll be a little bit easier for us to get there, so we're really looking forward to it next year. We'd like to thank everyone from home, from NUI Galway within the College of Engineering, and from Shell Ireland, and from all our local company sponsors in the west of Ireland and around Galway. Thank you very much, because this would not have been possible without you.
We had 3 aims when we went to Shell Marathon for the first time. First aim was to build a car and get to Shell Marathon. Second aim was to pass technical inspection. So before you're allowed to race on track, you've got to prove that your car is safe and is complying with the rules, so you don't have any extra batteries hidden in your car or anything like that. We did that. The third one was to get a score on the track, to get a score on the board. So we completed several successful runs. I got a score on the board, and the secret aim, the bonus secret objective, was not to come last in the thing. So in fact, the result was that we got a score of 287 kilometers per kilowatt hour, which put the Geec 23rd out of 51 electric prototype class. These students from NUI Galway, on the first attempt by any Irish team to race at Shell Marathon, came on the top half of the scoreboard. So we were ecstatic. We were pretty happy with that. What does that score mean? 287 kilometers per kilowatt hour. Well, a kilowatt hour is a unit of energy. It's the unit that's used on electricity bills. So when you pay your electric bill, you're paying a certain number of cents per kilowatt hour. So for every kilowatt hour of electricity drained from our battery, every kilowatt hour of energy, this car could complete 287 kilometers per hour. That's not the unit that's used for traditional fossil fuel burning cars. You'll be used to hearing miles per gallon or litres per 100 kilometre. So an ordinary, petrol or diesel car does maybe 30, 40 miles per gallon on a good day. A small car will do a bit better than that. A very small car, a hybrid car, might do 80 or 90. If you convert our kilowatt hours into the equivalent energy that you get from burning a gallon of diesel, you can work out that this score is about equivalent to 8,000 miles per gallon of diesel. So it's about 200 times more efficient than your typical car on the road. So this is a very efficient machine. This was a phenomenal achievement, and it taught us that we had to set our aims a bit higher in future. But why was the Geec so good? If you look at this picture here, you can see in the background some cars that look a lot smaller and a lot more exotic, and that the beautiful Geec looks a bit rough and ready, really, in comparison. And in fact, it was a heavy car. It was over 80 kilos in weight, I think, and the lightest car at the race was under 30 kilos. But we did some things very well. If you look at if you look on the left, here is one of the classic Shell Marathon cars, and the car that was the world record holder for energy efficiency for many years. And compared to the Geec, it's very narrow and it's very tall. So it has excellent aerodynamics. but it has terrible stability because it's high and narrow. And we looked at a lot of video of cars on the Rotterdam course before we went there, and we found a lot of scenes like this.
Is it on the phone?
Are you okay?
So the team learned from this that cornering is critical, and rollover in cornering is a critical problem for an eco-marathon car. Unlike, say, a Formula 1 car, where sliding in a corner is the thing that limits the speed, for these cars it is rollover that limits their speed in tight corners. And that's a big problem when you're trying to be efficient, because every electric motor and every internal combustion engine has a particular speed at which its efficiency is highest. And a big part of the design of these cars is ensuring that you always use the motor at that speed or very near that speed. If you have to slow down to get around corners safely, it's bad for two reasons. One, you might have to use the brakes to slow down, and using the brakes is a disaster because ordinary brakes at least just turn precious energy into heat that you can never get back in a useful form. The second reason it's bad is that when you come out of the corner, you have to apply power to get back up to your design racing speed. And that means you're using your motor at that low speed where it's no good. So there's a story in this about what engineering is and what engineering isn't. So to make a car that doesn't roll over, you could look at some other cars, you could decide to make it a bit wider and a bit lower, make some guesses. You might get lucky, it might work. But that's not engineering, and it wouldn't necessarily be a good car. Engineering is when you bring science and analysis into this to make the design good. And any design that you do, you are making choices. So in this designing this car, for example, the students have to choose how long should the car be, how wide should the car be. Things that seem as trivial as that actually have big consequences, and there are good choices and bad choices. And this sketch here is by a student from 2014. It's one of the very first bits of analysis that was done on the Geec. And it's this TR is the width of the car between the front wheels, WB is the wheelbase, the length between the front wheels and the back wheels. The centre of gravity is here, and there are forces. These black arrows are forces that act on the centre of gravity. And this is the beginning of an analysis to work out what makes the car roll over and how you design a car that will not roll over. Now this is a fourth year project that was done on the Geec in 2015, and you'll all do one of these in fourth year or fifth year. It was the culmination of your degree, and it's one big piece of work where you go into real depth and you become an expert, a real expert on this topic. And the fourth years on the Geec team, they normally do their final year projects on the Geec, and they are the ones who are driving the design and doing the real deep design problems. So let me try to find the right page here. This analysis begins with something that will be familiar to you if you've done applied maths already. If you haven't done applied maths already, you will be familiar with this pretty soon. These are free body diagrams of a generic car. They're diagrams that show forces, just like the sketch I showed you a minute ago. Okay, and there's a centrifugal force when you go around the corner. That's what tends to push the car over and make it roll over. And there are weight forces, and there are actually reaction forces where the ground pushes up on the wheels, and it's the interaction of all these forces that makes the car roll over. So this student did the analysis here, took the diagrams, turned the diagrams into equations, solved the equations, did the maths, and so on and so on and so on, and eventually came up with a really nice result, which is summarized in this graph here. Now, this graph is interesting, and this is the graph that tells us how to design the car so that it doesn't roll over when it's driving at 7 meters per second, which is close to our design speed for Ecomarathon on a turning radius of 8 meters, which was the tightest corner on the Rotterdam circuit. The x-axis on this, A over L, is the position of the center of gravity or center of mass. Okay, a high value means that it is at the back, and 0 would mean that it's right over the front wheels. Okay, the vertical axis is the height of the COG. No, it's not. The vertical axis is the width of the car. The higher we are on that number, the wider the car is. These numbers here are the height of the center of gravity. The bigger that number is, the higher the center of gravity is. Okay. So say, how do we read this graph? Well, say we have a value of 0.4 here, which means the center of gravity is 40% of the way from the front axle to the back axle. So we go up along this line and say we have a car that's very wide. It has a width parameter of about 1.6. Okay, so this is our car. This is a design. So what this graph tells us is that we're between 0.4 and 0.5 on these height contours. That is saying the center of gravity needs to be at 0.45 or below in order to corner safely without rolling over. So this is a design calculation. It's telling us the interrelationship between length and width and a height of the center of gravity to avoid rolling over. So if, for example, if the center of gravity is very near the front of the car, if we're over here, then and we have the same width of car, then we can get away with a higher center of gravity. Then we can get away with the center of gravity as high as 0.6. If the center of gravity is very near the back of the car, over here, we have to have a very low center of gravity. Why is that? Because there are two wheels at the front and one wheel at the back. If your center of gravity is right over the back wheel, it's like a unicycle. The front wheels are doing nothing for you. You're trying to balance on that one wheel all the time. So the further in this three-wheel setup, the further back the weight is, the more unstable the car is. So this gave us, on paper, the ability to lay out the car and get the major dimensions of the car right, so that the car could get around corners without having to slow down. And that was the tactic for that first car. And it's actually a tactic that has stuck with the Geec ever since. And that's using science and doing the analysis to make sure the design does what we want it to do. Did it work? It did. If you see in the video here, this is the same corner that we saw a car rolling on earlier. Here's the Geec charging through at pretty much constant speed, and you can see that it's overtaking other cars as it goes through that tight corner. So in Rotterdam, Geec was able to cruise around the track at pretty much constant speed, pretty much on its ideal design speed all the time. And the Geec wasn't the only team to think like that. Looking back to your classic SEM car here, number 1, the tall narrow car, we went with a lowish wide car, but the winners of Shell Eco Marathon that year had a low wide car, and one of the first cars of this shape, with the front wheels spaced out really wide in their own aerodynamic enclosures, and the main body of the car is very narrow and very low. So those ultimate winners also had the same idea of getting that center of gravity down and making the car wide so that they could corner at any speed they wanted to, practically. Not only that, but meanwhile, while the NUI Galway team was getting the Geec ready, part of the team was starting to design the future Geec, and one of their design concepts before they saw that car from Munich, one of the Geec future design concepts looked a lot like it. It had a narrow center body, and it had its front wheels out wide on this sort of outrigger setup with their own aerodynamic fairings. And this was part of an aerodynamic study. So by then, and following the success in Rotterdam, the Geec committed to this low-wide design and began to look at the aerodynamics. And this shape was just one of the shapes that the aerodynamic designer considered. There are two extremes. One extreme is this shape with the external wheels, and the other extreme is this shape where you bring everything inside the aerodynamic package, and then you try to make that package, it's going to be a wide package, but you try to make it as smooth as possible. So that was concept 1, which gave you a drag of 2.3 newtons. Concept 3 was the external wheels, which gives you a higher drag, actually. Now this is according to computational models. Okay, the pictures that you see here are with a technique called computational fluid dynamics, which can solve the equations of fluid flow to figure out how air moves around the car, or around any shape. Now that's not an exact result. There's a lot of science and a lot of craft in using that technique to get good results, but it gives you, it's another kind of analysis, it's another kind of science that you bring to the design. And then there were a whole bunch of hybrid concepts in between, where you kind of blend the body in with the wheels somehow. But it turns out that the very best design was this one here, this final one at the end, which is very close to the fully enclosed body, that big wide body, which is surprising. So it turns out that if you're going to have the wheels out wide, the best thing to do is basically have a very wide but very smooth shape that covers everything. So that first run of the Geec taught us that we should set our standards higher, and that the work that NUI Galway students were doing was as good as the best in the world, literally. So the next team, the team building the 2015-16 car, made an absolutely huge effort and built an almost completely new car, sticking with this low and wide design philosophy. New chassis to fit inside that, new aerodynamic shape, testing, as you can see there in the car park up in Dangan, and building the aerodynamic bodywork for this car, which was an absolutely enormous job. And the results were amazing. They made this beautiful, beautiful piece of engineering. Look at it. Look at that car. It's beautiful. So this car went to London, London Olympic Park, raced on a circuit around the 2012 Olympic Stadium. Absolutely spectacular setting. The car did really well. Big difference between London and Rotterdam is Rotterdam doesn't have any hills. This track in London had a horrendous hill, and you see the car just approaching it now. The team knew that. They had to map the track. Just about now you're going to hear some cheering, which is the team, or most of the team, standing on over the circuit there watching the car go by. Going up that hill that had to be designed for, that drew a lot of current from the motor, made the car run at very low speeds, made the motor get very hot. You see quite a few cars did not make it up the hill, especially on the first attempt. Just on the right hand side there you can see the Olympic Stadium. 2016 the car came 21st, slight improvement. 2017 the race was again in London. The car was much improved. Same basic car as 2016, but a lot of work done. And this is what happened.
3, 5, 4, yes!
So 354 kilometers per kilowatt hour. That's a big jump from 287 in Rotterdam and on a much tougher course. And that result was 13th in Shell Eco Marathon Europe. So that is world-class engineering and racing by any standards. This would be a good time to say a bit about the Geec's drivers. They've always been engineering students, and they've always taken an engineering role in the team. Most of them have gone on to be design team leaders in their 4th year. They work really hard on testing and setting up the car, as well as doing their engineering jobs. When they get into the car to race, they are seriously racing and they do not mess around. So, the average speed is 25 kilometers an hour. It might rarely get up to 40 kilometers an hour going downhill. So it's not Formula One speeds, but it really is racing. Let me show you an example. This is London in 2018. Niamh is coming up to the most difficult corner on the track, and she has a lot to do. So she's driving to a plan which is aiming to give an average speed of 25 kilometers an hour. You don't want to go much faster than that because you get more aerodynamic drag, which sucks up energy. The plan will call for an average of maybe 27 to give a small margin of error. But she can't keep a constant 25 because she has to go up and down hills. So there are very specific points on the course, waypoints on the course, where she has to set her speed to certain levels and put the power on and take the power off. She's listening on the radio to the team who are telling her if she's ahead or behind schedule, lap by lap. She is watching the car for things like overheat warnings. She's listening to the car for signs of trouble. So she's doing all this engineering in her mind, and she's also handling the car on track, watching her lines through corners, trying to find the best lines through corners so that she doesn't waste energy by steering too hard. And she's got to do all this without using the brakes. Okay, so it's a real game of chess here that the drivers have to play. Now, to complicate things further, she is coming up behind another car and she's looking for a way around. Every car will drive on a different plan. They're all trying to get that 25 kilometer an hour average, but they will all have slightly different plans for making that happen. So they'll be at different speeds on different parts of the course. And Niamh is coming up behind a car that happens to be going a bit slower on this part of the course. You'll hear a lot of honking of horns, and of course the drivers have mirrors which they're using as well. So there's a surprising amount of non-verbal communication going on here between drivers. So let's see what happens. Now, drama, there's another car ahead and it's going much slower. So it might be an internal combustion car, because they tend to run their engines for very short bursts and then freewheel down to very low speeds and accelerate up again. But our pair here is closing in fast on this car, and they are about to come into the most critical part of the corner. And somehow they all come through it. They find space, and Niamh comes out in front of the group with a clear track ahead. So absolutely amazing stuff. So before I finish, one more engineering story from the Geec. And there are lots of engineering fields involved. There's all the electrical side and electronics. There's the structures, the energy management, the mechanical component design. But aerodynamics is the one that I'm talking about just because it's the one that I know best, and I guess the one that I like best. So one thing we didn't consider in the first few years of aerodynamic design was the effect of the wheels. And in all the computational models of aerodynamics, it was imagined that the car is glued to the ground. The car is flush with the moving ground. There's no gap, but of course there is a little gap between the bottom of the car and the road, and the wheels stick out through that gap. So one of the students in their 4th year work took a closer look at this, And what you're looking at in these pictures is a view of the bottom of the car as if you're under the car looking up, and we're looking at streamlines of airflow coming from top to bottom, from the front to the back of the car. On the left hand side is the old model where there are no wheels and there is no gap between the floor and the ground. You get 2.84 newtons of drag. On the right hand side is the updated model where there is a gap between the floor and the road, and the wheels are in that gap, and the flow is a mess. There's lots and lots going on in that gap, and the drag is almost twice as high. It's almost 6 newtons. Okay? There's a lot going on there, and it seems that these wheels sticking out through the bottom of the car almost double the aerodynamic drag on the car. Again, there's a big health warning on this. It's computational modelling, so it's not perfect. To get to the real truth of this, you would have to go into a full-scale wind tunnel, but this is the next best thing. So Tom Dillon, the student working on this, came up with a solution in 2 stages. The first part of the solution was simply this. We'll take those fairings, those cavities that the wheels are in, and we will close them off as much as possible. We'll put a floor on that cavity, which you can maybe see here. And the front wheel, that's easy enough on the back wheel. You just cut a slot, but for the front wheels, they have to steer. So you have to cut a hole out of that cavity. You have to cut a hole out of that floor to allow the front wheels to move and steer. So that means you're still making a big hole in the car. The really clever part of this was what Tom invented next, which was to attach a movable floor to the steering mechanism. And that allows you to close off a lot of that hole. You can't close it off perfectly because there isn't enough space, but you've closed off a lot of it. And he did the computational models to show that that reduces the drag quite significantly. Now, at the event at Shell Eco Marathon, they have the competition for pure energy efficiency, but they also have some awards and prizes for technical innovation and for design and for the quality of the engineering work. So this piece of work got the judges' attention in 2018, and this is what happened.
Right, so the winner of the Technical Innovation Award used an effective and simple approach to lower the undercarriage aerodynamic drag of the steering wheels of their prototype vehicle. So the Technical Innovation Award winner and is invited on stage is Team 330, National University of Galway. Come on up.
So how can you get involved? Well, every year new people join the team. We try to keep 20 to 30 students on the team. 5 to 8 maybe join from first year each year. We will have some application process for that, and you'll hear about it. Now, nobody is quite sure what will happen this year. It might be a good chance to do a lot of design work for the next generation of the Geec. We don't quite know, but the Geec team will operate this year, and the Geec car will roll again and race again. Maybe not this year, but it will race again. And you can be a part of it. You can be a part of this, really the sheer joy of engineering and of just doing something really well as a team. That's what this is about. There are some bad days as well, okay? The team sucks them up. There are days when the driver has to walk home carrying part of the car. Not many of those days, but nothing about this is easy, but the rewards are absolutely worth it. These are the lecturers who are involved in the Geec: Rory Monaghan, Martin Glavin, Maeve Duffy and myself. You will come across them as you go through college here. You can join the Geec if you're in mechanical engineering, energy systems engineering, electrical, electronic engineering, or electronic and computer engineering. Those are the domains that the car needs. Thanks for listening. I hope I've given you a taste of what this is about. And I hope I've shown you that the foundations matter. Studying engineering is not always going to be fun and exciting, if I'm being honest. But if you master your forces and velocity vectors and voltage and current, if you master the fundamentals in this first 1 or 2 years, you can build on that and you can go anywhere. The lesson of the Geec is that you can pick a field and you can be the best in the world at it in engineering. Even as a student, you can be world class at what you do. So very best of luck to you in your engineering studies. Don't hesitate to contact any member of staff for a bit of support or to answer some questions. And I look forward to seeing some of you over the next 4 or 5 years. Good luck.